Imagine a basin so flat it feels invented, a perfect white sheet of mud, a rim of black cliffs, and a sky so wide it makes you breathless. This is Racetrack Playa in Death Valley National Park, a place of stark geometry where the sun burns, the wind scours, and, for reasons that baffled generations, stones sometimes leave long, mysterious trails across the surface as if guided by invisible hands. For decades, the sailing stones, also called wandering stones, captured the imagination. Heavy rocks, some weighing tens or even hundreds of kilograms, lying in quiet clusters by the cliffs one season and dragging slow scars across the playa the next. These trails, sometimes straight and sometimes curving, sometimes intersecting, sometimes solitary, are a desert's handwriting, a record of events we rarely witness but desperately want to explain. The question is simple: what moves them? The storytelling begins here, at the pale floor where wind, water, ice, and gravity meet. The history of a riddle from prospectors to modern science. Reports of moving stones date back over a century. Early visitors sketched the tracks and wondered if hoaxes, strong winds, magnetic forces, or even supernatural causes were at play. The place collected legends, and scientists collected hypotheses. Was it powerful gusts ripping rocks across the mud? Were dust devils to blame? Were the stones embedded in thin sheets of ice and carried like miniature continents? Over decades, observers mapped trails and debated mechanics, but direct observation eluded everyone. The events are episodic and depend on the right combination of rain, cold, still water, freeze, and thaw, rare in an already rare climate. The 2013 to 2014 campaign, Instrumentation Meets Patience. The story turns from speculation to method in the winter of 2013 to 2014, when a carefully planned field campaign succeeded where guesswork had failed. Scientists deployed time-lapse cameras, a weather station, and GPS-instrumented boulders across the playa. They waited. The winter brought an unusual set of conditions. Rain filled the playa's shallow basin, nights were cold enough to freeze the pond, and days warmed enough to break the ice into panels. When the ice fragmented and the sun coaxed meltwater beneath, thin sheets of floating ice, sometimes only a few millimeters thick, came alive under light winds and began to drift. For the first time, cameras captured full movement events, rocks that had sat immobile for years being nudged again, and then sliding across the slick mud, leaving the long, straight trails that had confounded observers for a century. These were not giant walls of ice smashing things, nor were they mythical levitations. They were delicate, ephemeral window panes of ice pushing and shepherding rocks in a choreographed, low-energy dance. What the instruments recorded: the anatomy of a move. The instrumentation made the invisible visible. GPS loggers recorded minute displacements. Time-lapse sequences showed thin ice panels moving at a few meters per minute, and parallel trails confirmed that multiple rocks, tens of meters apart, could be shoved by the same moving ice sheet. Observers documented rock speeds of roughly 1 to 5 meters per minute during brief episodes lasting a handful of minutes to tens of minutes. And in at least one spectacular winter event, more than 60 rocks shifted positions, some traveling tens to hundreds of meters across the playa, all while the sky was calm and the wind was light. The tracks were often nearly parallel, revealing the action of a broad, coherent ice sheet rather than chaotic winds acting on individual stones. The combined evidence, video, GPS, and weather data, closed the long debate in an elegant way. Thin, floating ice panels, driven by gentle winds, pushed stones across a lubricated soft surface, forming the familiar trails. Explaining the mechanics: ice, wind, and the wet mud's slipperiness. The physics is at once simple and subtle. First, you need water. enough precipitation to create a shallow pond across the playa surface. Second, the temperature must drop sharply at night so that the pond freezes into thin sheets of ice. Third, the morning sun, not a gale, warms the ice and underlying mud, allowing the ice to fracture into panels that float on a film of meltwater. Light winds, sometimes as gentle as a few meters per second, then push these panels across the playa. Where a panel catches on the upstream side of a rock, it exerts distributed force across the stone's face. The slick mud dramatically reduces friction. In this low-force regime, even a modest pressure over a broad contact area can propel a heavy rock. The result is a smooth translation: rock plus ice plus wind equal motion. Trails, tests, and the visual drama of evidence. Listen, the playa is a silent script. The trails are lines of historic movement, an archive of events that once occurred when the desert briefly became a shallow, freezing lake. Getting close to the tracks, you see variations, deep grooves, faint scratches, sinuous curves where wind shifted direction, and sometimes abrupt terminations where the panel's shove stopped. Each trace is a palimpsest, a record overwritten by later motion, wind scouring, and seasonal drying. Reading these lines is an art and a science. Geomorphologists record widths, depths, and orientations. Hydrologists model the pond depth and melt rates, and physicists test how distributed pressure translates to rock acceleration. Taken together, these readings let us reconstruct individual moves with impressive fidelity. The visual spectacle comes from the juxtaposition: a barren white field, rocks cast like relics, and long black signatures curving away like calligraphy. The explanation is elegant, but open questions remain. What sets the size distribution of stones that move in a given event? How often do the right conditions recur across decades and centuries? And how might climate change alter that recurrence? Are there microenvironmental differences across the playa that bias movement to particular clusters? And philosophically, why do such simple, low-energy processes yield such striking geomorphic signatures? Continued monitoring and modeling answer these questions, and as data sets grow, we gain predictive power. Researchers can estimate the likelihood of movement in a given winter and predict probable run-out lengths for rocks of various masses. If the secrets of the planet excite you, subscribe to Discovering the Unknown. We bring deep research and cinematic storytelling to the mysteries that shape our world, from stones that sail across deserts to the forces that turn continents.